So conjugacy in the symmetric group may not be pretty. It may not be easy to count, but yet it's deterministic, right? If we are good enough at combinatorics, we can understand the partition function, which will tell us how many conjugacy classes there are in the symmetric group. And then if we're skilled enough at counting in combinatorics, we can count how many elements are in each one of those conjugacy classes. But the nice thing, again, about Sn is that cycle type completely determines conjugacy class, in the sense that two elements are conjugate if and only if their cycle type is the same. That's conjugacy in the symmetric group. But it turns out that in the alternating group, which is the index 2 subgroup inside of Sn that's made up of the even permutations, inside the alternating group, conjugacy is not quite that simple. It is still true that two elements that are conjugate will have the same cycle type, because the elements in An are still elements in Sn. But the converse statement may not always be true. Two elements of the same cycle type in An are conjugate by an element of Sn for sure, but are they always conjugate by an element of An? So the question of conjugacy in the alternating group is a little bit more intricate, and in this video we'll take a look at what that means. So An is a little more difficult than Sn because conjugacy class is not completely determined by cycle type anymore. Recall that in S4, the 2 plus 2 cycle 1, 2, 3, 4, and the 2 plus 2 cycle 1, 4, 3, 2, we showed directly we're conjugate through the element 2, 4. Just by swapping 2 with 4, we achieve the relabeling that we need to turn sigma into tau. So we showed that before. But this element 2, 4 is not enough to show us that these two elements are conjugate in A4. Why? Because 2, 4, the transposition 2 and 4, is not an element of A4. It's an odd permutation. So the question of whether sigma is conjugate to tau in the alternating group can't be answered by the proof that we just showed. Instead, if we were to show that sigma and tau here are conjugate in A4, we would need to find an element of A4 which conjugates one of them into the other. Luckily for us, there is such an element, but it's not 2, 4, it's 1, 3, 4. Let's check it. If I conjugate sigma by 1, 3, 4, so multiply by 1, 3, 4 on the right, and the inverse of 1, 3, 4, which is 1, 4, 3, on the left, then let's check to see if we get tau. So applying 1, 3, 4, reading from right to left to 1, 2, 3, 4, gives me this. Then applying the transposition sigma, the pair of transpositions, and then applying 1, 4, 3 to the result. Indeed does give me, at the end of the day, the transposition, 2 plus 2 transposition tau. So for this pair, the cycle type was actually enough. We could find an element of A4 that conjugated sigma into tau. So great. So it looks like for this example, cycle type was enough. But that's not always going to be the case. In fact, this is a theorem we're not really going to prove, but the splitting criterion tells us when cycle type is enough in the alternating group. And the theorem says that cycle type is enough when that cycle type contains a cycle of even length, or when it contains two cycles of equal length. And this is counting cycles of length 1 as the fixed symbols. So as an example, in A4, 1, 2, 3, 4, and 1, 4, 3, 2, the example we just looked at, these were conjugate. Actually for both reasons, because they contain a 2 cycle, a cycle of even length, and they also contain cycles of equal length. Each of them is a 2 plus 2, so there's repetition. So in another example, if we look at the group A7, these two permutations are also conjugate. They have the same cycle type, for starters, and they happen to contain 2 cycles of equal length. Each of them has a pair of 2 cycles. Also, we could have satisfied the first criterion as well, because each has a 2 cycle, therefore it has a cycle of even length. So this actually takes care of most cycle types that we can have inside of An, but it doesn't take care of them all, because there will, in general, be in An permutations that are made up of odd cycles of distinct lengths. And again, we're counting fixed symbols here as cycles of length 1. So as an example, inside of A4, we have the 3 cycles, which we're going to count as 3 plus 1 cycles. And since 3 and 1 are odd and distinct, this is going to satisfy our splitting criterion. And just to justify what's happening, so here are the 8 elements that are the 3 cycles in A4. The elements 1, 2, 3 and 1, 3, 2, it turns out, are not conjugate in A4. In order to conjugate one of these into the other, we really do need the permutation 2, 3, which is not an even permutation. So those two elements are not conjugate one to another in A4, even though they have the same cycle type. However, 1, 2, 3 and 1, 2, 4, yeah, that one's fine. We can actually achieve that conjugacy inside of A4. So these 8 elements actually split into 2 conjugacy classes in A4. And the good part about this theorem is that it tells us exactly what happens when these conjugacy classes are splitting, that they always split into just two conjugacy classes. Let's look at some basic examples to get a feel for how this works. A2, A3, and A4. What we're going to do is first of all list the possible cycle types of elements in these alternating groups, and then we'll find out which of those cycle types leads to a split conjugacy class, a pair of conjugacy classes. Again, those are the ones with distinct odd cycle length. Starting with A2. Well, the only cycle type in A2 is 1 plus 1, so the only permutation in A2 is the trivial permutation. So A2 is the trivial group. That's really boring, so let's forget about A2. How about A3? Well, there are two different cycle types in A3. There's 1 plus 1 plus 1, and there's 3. 1 plus 1 plus 1 is just the trivial cycle, and then my three cycles are 1, 2, 3, and 1, 3, 2. So there are only 2 3 cycles here. But since the 3 cycles have cycle lengths that are all odd and there are no repeats, since there's only one cycle length here, it's 3, there's nothing repeated. Therefore, this cycle type, the cycle type 3, splits into two conjugacy classes. So one of these elements goes into one conjugacy class, the other goes into the other. And then the identity, of course, is always by itself in a conjugacy class. So A3 has 3 conjugacy classes. But notice what happens here. Every single element of A3 is by itself in its conjugacy class. Therefore, as we said before, every element of A3 here is going to commute with every other element of A3. Therefore, A3 is an abelian group. Not surprising, because we can check directly that A3 is isomorphic to Z mod 3. So neither of these two examples are particularly interesting. A4 is where we start to get some interesting stuff. The cycle types in A4 are 1 plus 1 plus 1 plus 1, 2 plus 2, and 3 plus 1. And we can list all those elements if we want to. Here they all are. All 12 elements of A4 fall into one of these 3 different cycle types. And of these cycle types, only 3 plus 1 satisfies the splitting criterion, that all the lengths of our cycles are odd and that there are no repeats. Therefore, this cycle length, the 3 plus 1 cycles, as we saw in the previous slide, does split into two conjugacy classes. But the other cycle types don't split. So the 2 plus 2s and the 1 plus 1 plus 1 plus 1s form conjugacy classes of their own. So in A4, there's a total of 4 conjugacy classes. You'll also notice that if I take the first and second conjugacy classes I've listed here and I take their union, that I actually do get a normal subgroup of A4. In fact, it's a normal subgroup that's isomorphic to Z2 cross Z2, the Klein 4 group. But what about A5? This is where the plot really thickens. So we saw A2, A3, A4 were fairly simple as it came to their conjugacy classes and their normal subgroups. But in A5, how many conjugacy classes are there, and how big are they? This is work that you're going to do in maybe a day or two in class, so I want to leave the bulk of this to you, but just to get you started on this, let's pick one of the cycle types in A5, say 2 plus 2 plus 1, and all of its elements look like a 2 cycle times a 2 cycle, and then there's a hidden 1 cycle at the end that usually we don't write. Well, how many different cycles like this are there? It's a combinatorics question. Well, for the first 2 cycle, I have 5 symbols to choose from, and I get to choose 2 out of them to permute. So there's 5, choose 2, 10 different possibilities for that first 2 cycle. Then after I've chosen those 2 elements, I only have 3 left to pick from to make my second 2 cycle. So there's 3 choose 2, or 3 possibilities for that second one. And then finally, the 1 cycle is determined at that point. I only have 1 possibility for what to put there. So it looks like there are 30, 10 times 3 times 1, different elements of this cycle type. But not all those elements are distinct permutations, because disjoint cycles commute one with another. That means that I get the same element of A5 if I transpose these 2 cycles that we found. So I really have to divide everything by 2. So the number of elements of this cycle type, 2 plus 2 plus 1, is 15. In fact, we can list all of them up here. So the first step toward understanding the conjugacy classes in A5 is to figure out what are the cycle types, and then for each of those cycle types, figure out how many elements there are of that cycle type. And that is a combinatorics argument, which is not too delicate. If you're familiar with binomial coefficients, then that should be enough to get you through. But it turns out, and you're going to fill in these details, that once we understand all the conjugacy classes in A5 and how many elements there are, you can actually prove quite immediately the following theorem about A5. And the theorem is that A5 is a simple group. In other words, there is no normal subgroup in A5 that is not trivial or the entire group. So there's nothing in between A5 and the trivial group that is a normal subgroup in A5. This is really, really important. This turns out to be the reason that we embarked on this review of group theory in the first place, because of how this is going to serve our needs this semester. It gives us a couple of corollaries. Well, we might be tempted to say, well, if A5 doesn't have any normal subgroups, and that means S5 doesn't. But that's not quite true, right? Because S5 has A5 as a normal subgroup. And there are other normal subgroups of S5, but particularly where we want to go with this is we want to think about what this means about the solvability of these groups, and not just the simplicity of these groups. So there are other normal subgroups of S5 besides A5, but there are no normal subgroups of A5 besides A5 and the trivial group. And the real corollary, the big one that we need, is that this implies that A5 and hence S5 are not solvable groups. Haven't heard that word for a while. But that A5 and S5 are not solvable groups has major implications for our study this semester. And in the Galois theory that we're going to get to, this is one of the biggest clues of all, that when we go from alternating and symmetric groups on 4 symbols to alternating and symmetric groups on 5 symbols, suddenly we lose the property of solvability that we could take for granted with fewer symbols. After all, A4 is indeed a solvable group, because it has that Klein 4-group subgroup, which is abelian, and so the quotients here, Z2 and the Klein 4 group, are indeed abelian quotients. So A4 is solvable, but A5 is not. And if A5 isn't, then S5 isn't either. So this is a big deal. The non-solvability of A5 is going to have far-reaching implications in our study, and it's going to really unlock the main theorem of the semester, which is that there is no formula to solve a general 5th-degree polynomial in simple radicals. So let's take a quick stock at where we are at the end of our intensive review of group theory. So the really big new concepts that we introduced here that may not have been in an Abstract 1 course are simplicity and solvability, and they all fit together in the following way. Among the class of all solvable groups, every abelian group fits into that class. Every abelian group is solvable, but certainly not every solvable group is abelian. We've seen a number of examples, for instance, the dihedral groups that are solvable but not abelian. Then on the other hand, we had the simple groups. And it turns out there's not a lot of overlap between the simple groups and the solvable groups. As you can prove, the only overlap between simple groups and solvable groups are the cyclic groups of prime order. So only Z mod P is both simple and solvable. Everything else is either one or the other or not both. Meanwhile, there are examples of abelian groups that are not simple, like cyclic groups of composite order, like Z mod 12, or direct products of cyclic groups, like the Klein 4 group, Z2 cross Z2. They're definitely abelian, and therefore solvable, but they're not simple groups, because they have non-trivial normal subgroups. Meanwhile, there are examples, as I mentioned, of solvable groups that are not abelian, like any dihedral group, Dn, if n is greater than or equal to 3. Also, S4 is a solvable group, the symmetric group on 4 symbols. Again, why? Because it has A4 as a normal subgroup with abelian quotient Z2, which has Z2 cross Z2 as a normal subgroup with abelian quotient Z3, which then, because that last group is abelian, its quotient goes down to the trivial group as Z2 cross Z2. So S4 is a solvable group. But according to the last slide, and according to the details that you are going to supply, A5, the alternating group on 5 symbols, is a simple group. And therefore, because it's simple and it's not Z mod P, it's not solvable. Which means that S5 is really left out here in the cold. S5 is not simple, it's not abelian, it's not solvable, which is the really important part of all of this. So in a real sense, this concludes our intensive review of group theory. It's taken us maybe 7 classes and 20 videos or so to get through all of this stuff. But at this point, we know probably as much as we need to know about the theory of groups to really power our study for the rest of the semester. And again, the really important conclusion of this video is that we have now come up with the tools to show that there are some really important examples of groups out there that are not solvable. And at the top of that list is the symmetric group on 5 symbols. S5 is not a solvable group. Shelve that away. Keep that written in a very prominent place in your notebooks, because that's a fact that we're going to use later on in the semester as one of the main components to help us prove that 5th-degree polynomial equations are not in general solvable by simple radicals.